I'm Mike from MotoIQ, and for this video we're going to do an engine that I have a lot of fond memories of, and I always wanted to build a really killer one for myself, but I have a love-hate relationship with it because it kind of sucks a little bit. But we're going to build a really cool one. We're going to fix a lot of the problems with this engine with modern technology, and I guess let's get into it. So this is a 4AG 20V. It's the last variant of the 4AG that came out, and it has the uniqueness in it that it has a 5-valve per cylinder Yamaha cylinder head, which makes it really cool and unique, and it's one of the reasons why I wanted to build one. Now the 20-valve version of the 4AG, believe it or not, is not the most powerful one. Stock to stock, yes, it's more powerful than the 16-valve 4AG, but when you really get into them, the lifter buckets are a really small diameter, so it limits how big of a cam you can run, and thus a 16-valve, when it comes to peak power, can make anywhere from 5 to 10 horsepower more, just because you can get better valve events with the 16-valve with the bigger followers. However, with the 5-valve is more valve area. So for a lower RPM engine, where you have a cam with lower lifts, the 5-valve actually has more valve area and makes more torque. So the 5-valve has more torque and a broader power band. The 16-valve has the potential to have more peak power. This is kind of going to be kind of like a mess around car, so I'm not really interested in building the most powerful 4AG ever. So I think I'm kind of building it to make a decent amount of torque for a 4AG. Now you see a lot of parts on the table, and there's a lot of parts under the table, and we're going to be talking about a lot of parts. And the 4AG is probably one of the engines that has the worst ROI of any commonly modified engine. I mean, you could spend a lot of money on these and not make that much power, but that's not really the charm of the engine. A lot of it is it goes in the A86, which is a really fun chassis to drive. You know, it revs freely, it sounds great. So it has a pretty good tactile experience. It's not super crazy fast though, even when you've spent a lot of money on it. So we're going to build something that makes a lot of power for a 4AG, but it's not like a Honda K motor or anything. So one of the things about the 4AG is it's a little 1600cc engine that's kind of small, so that's not really going to make impressive torque or power numbers. So we're going to like punch it up to get more torque. So we're going to like bring it up to a little bit more than 1750 cc's. I think if you do the math, it's 1753 or something like that. To do that, we're getting an MRP crank. This is an MRP stroker crank. MRP is a company in New Zealand that probably is one of the more cutting edge companies when it comes to 4AG development. Now, my base development on the 4AG stopped in the late 80s at some time when I left TRD to go to Nissan. So my knowledge was a bit behind, but Barry at MRP was very helpful in helping me piece together this pretty killer one. The MRP crank is 83 millimeter stroke, up from the stock 77. It's fully counterweighted, so you don't have out of balance stresses going through the crank. The full counterweights kind of helps the fatigue strength and helps the crank stay together at high RPM. It's made out of 4340 alloy in a forging that's final machined. It's a really nice piece. When you look at it, it has rolled fillets in the corners of the journals, which is really good for fatigue strength. It has chamfers in the oiling holes to kind of help to act like a little oil reservoir. It's a trick that we usually do on cranks, but MRP's done it for us. You know, it's all the right stuff, the right material, the right construction. It uses the larger journals from like the later 4AGs, like the supercharged ones, so you have more rod bearing area. It's a really nice crank. When I used to work at TRD back in the day, this is a better crank than what we used in like the GT and the Formula Atlantic cars. To give it the most durability possible, we cryo-treated it at CTP Cryogenics. Cryogenic treating converts like a lot of the residual austenite in the metal into martensite. So we're going from a body-centered cubic metallic structure to face-centered cubic. Martensite is stronger, harder, has better wear characteristics. Now, if you've seen some of our videos on the results we've had with cryo treating, it's actually pretty amazing, and you know, like I really believe in it now. I was skeptical about it up to a few years ago. Then we started doing it in some of our racing customer engines. Now we have a history where we've done maintenance and teardowns on those engines, and the difference in wear and longevity is pretty mind-blowing, actually. So all my personal engines and all our serious customers, we're going to do cryo from now on, and I really recommend it. After cryo, we had this balanced, dynamically balanced, and then after balancing, we WPC treated it. So WPC treating is like blasting the part with little tiny ceramic balls at really high velocity. There's also like dry film lubricants and other additives in there with the media. So what that does is it puts a super smooth finish, and it actually does a stressed hardened skin over the part too, kind of like shot peening. And it also imparts that dry film lube into the surface as well. So what this does is by doing surface compression, you're increasing the fatigue strength quite a bit, probably about 100% over an untreated part, and you're also really reducing the friction. So cryo treating helps fatigue strength, helps tensile strength, helps wear, and WPC helps fatigue strength, reduces friction, and also helps wear. So the crank's been treated in this way, and you know, the crank failure has always been kind of an issue when you're trying to get a lot of power out of 4AG. Like the early cranks, like you know, we've had them fail in as little as 45 minutes of track time when you're winding them out past 9. And you know, with our treatments and MRP's good quality crank, well, we expect a lot more out of it. Kind of wish we had this crank back in the day. Next up is the MRP connecting rod. Now the stock 4AG connecting rod is 122 millimeters long, and the MRP is 127. So what this does is you still get the displacement of an increased stroke, but the longer rod gives you a more favorable stroke to rod length ratio. Typically, all the other stroker kits on the market use stock 122 millimeter length rods. So that leaves you with a stroke to rod length ratio of about 1.46, which is, you know, really terrible. The MRP combination gives you a stroke to rod length ratio of, I think it's 1.53 or something like that. So that's quite a bit better. When you have a low stroke to rod length ratio, you have a lot of angularity in the motor with the connecting rod. So that angularity wants to dig the piston into the cylinder walls, so you get more friction, more wear, you get more internal stress. Also, when you have a low stroke to rod length ratio, you have a lot of acceleration away from TDC, and that puts a lot of tensile stress on all the parts. It also doesn't give you as much time to fill the cylinder, so your volumetric efficiency also drops with a low rod ratio. So MRP kind of splits the difference between your typical stroker and stock. I think stock is 1.56 to 1 or something. I don't remember exactly what it is. It's really easy to figure out. So you keep a acceptable rod ratio, and you have your stroke with MRP. The MRP rod is a good quality rod. It's a CNC machine from a forging. It's a 4340 forging, good stuff. 4340 is a high nickel, high chromium steel alloy. So think of it as chrome moly, but with more nickel, so it's actually tougher. 4340 is good for cyclical stresses, and it's good for impact resistance. So this is the exact kind of stress a connecting rod sees, and the kind of stress a crank sees. So it's a very good material for rods and cranks. If you've been watching our videos, most of the cranks and rods we use are typically made out of 4340. So it's a real high quality, good alloy for this intended use. The rods have ARP 2000 bolts. They have a bushing for aluminum bronze bushing in the small end for good durability. And if you look, the pin oiling holes are on the side of the rods. I prefer this over your typical pin oiling hole at the top. My reason for this is the top of the rod is the highest stress part besides the bolts. And when you put a big hole in there, you're weakening it. So when you run two smaller holes, like in the bottom, like actually into the beam, you're conserving more strength up there. Now there's some very good quality rods that I use, high quality ones that have an excellent record that have the hole at the top. But if I'd have my druthers, I'd rather have two small holes on the bottom like this. The MRP rod also has a notch to help lubricate the thrust bearing, and it's shot peened after machining. Shot peening puts a layer of compressive stress over the part and improves your fatigue strength at least 100%. In addition, we WPC'd and cryo-treated the rods and the bolts to get every bit of strength we could. So this is a very stout reciprocating system. It gives you, pretty decent rod ratio, pretty decent piston speed for a stroker 4AG, and most of the ones on the market don't. MRP says this combo is good for 9,500 RPM, and we believe them. So we're pretty confident that this is going to hold up great in the RPM range we want to run in our little naturally aspirated engine. So for pistons, we had JE make us a really special piston. This is for the 20V, so it has 5 valve pockets. We had to make the valve pockets deeper than stock because we're running a pretty big cam. What we've done too is we've moved the piston pin way up into the oil ring area to accommodate the longer rod. And we're using a support rail for the oil ring. Support rail is like an extra ring that goes along the bottom underneath the oil ring that prevents the oil ring from falling into the piston pin hole. Some other special features, we're running 11.5:1 compression, which is about the stock compression for a blacktop, but with our California 91 gas, it's probably the most I dare go to be reliable. If you live in other parts in the country, you can probably get away with 12:1 or something if you can get 93 or even 92 with good tuning. But our gas is really horrible, and it's about to get worse with some new dumb laws that are coming into effect in July. So, wanted to be conservative. One really neat feature is this has JE's new radial gas ports. Now, this is something that JE has just come out with and patented this year. You might have seen it at the PRI show. They got an award for this, for a best original new product. And what it is, so you've probably seen a lot of gas ports where they, like on drag racing motors, where they drill holes in the top of the dome so you could feed gas behind the #1 compression ring to push it into the cylinder walls. That way you can run a really low tension ring but still get good compression seal. Well, that kind of gas porting tends to clog up, and is maybe a little bit overkill, and you get a lot more ring wear, so it's only suitable for drag racing. So what JE's done is they've kind of put these slots that feed gas into your conventional lateral gas ports. You can see it here. So this helps the gas get down to the number one ring a little bit better. Helps your ring seal, doesn't clog up, and doesn't put so much gas back there that your ring life is a lot worse. Now JE told me that this little difference is good for up to a couple % more power, believe it or not, and this little 4AG is going to need everything it can get, frankly. So we have these vertical gas ports. We have anti-detonation grooves at the top. These are these grooves right above the first ring. Now what these do, they do two things. One is they're kind of a labyrinth. So like any detonation shock waves kind of have this grid pattern to kind of buffer the pressure spike to the number one ring. And the other thing is when you get detonation, you have a lot of localized heating. And, what happens in pistons is that, above the number one ring, you get detonation, the metal really expands in that area, and you have scuffing and galling right there. Now, if you build a lot of engines, especially, like if you built a lot of pump gas turbo engines, trying to get all the power you can out of them, you've probably kind of seen this before. Like you'll see galling above the number one ring, especially if you see signs of detonation on the piston, like that kind of sandblasted look around the edge, particularly around where the exhaust valves are. And what these grooves do is they give the aluminum a place to expand into without making the thing get bigger in diameter. So it kind of reduces that tendency to gall up there and make a mess. So we got your vertical gas ports, your anti-detonation groove. You have another groove between the number one and number two compression rings. That's an accumulator groove. And what that does is it acts like a reservoir of high pressure gas to kind of help make sure the number two compression ring has a supply of pressurized gas to get behind it and help it seal better. So a lot of race pistons have accumulator grooves nowadays, but if you've ever seen that groove, that's what it's there for. This is also done on their FSR forging, so it's a strut type piston. It's really lightweight. JE is really good at coming up with the piston cam. Like a piston's not a perfectly round cylinder. It kind of has a asymmetrical shape to the skirt, and it's kind of curved, and they call that the piston cam. And your cam design is really critical to prevent scuffing and galling. It also reduces noise. So JE is really good with their cam design. So their pistons tend to run pretty quiet, even if it's a thin slipper skirt, strut type piston. I mean, you can see how narrow the skirts are, which is good for low friction to make more power. But in the past, these kind of skirts were noisy and made like slapping noise, so your engine would kind of sound like a diesel, but not anymore. JE has also made this piston out of 2618 low silicon alloy. 2618 is really tough and ductile and can take a lot of stress. The disadvantage of it is it has to run a bigger piston to wall clearance. So in the past, it tended to be noisy, especially with cold startup. It would be kind of clattery till the engine warmed up, and then it would still probably be noisy even then. But like I said, JE has they're really good at thermal analysis, and their cam designs are really good. And I've actually found their 2618 pistons to be pretty darn quiet. They're not perfectly quiet like a stock piston, but you really have to listen to be able to hear that startup clatter. And a lot of people might not even notice it. The last feature I want to talk about is offset piston pin. Now you can kind of see it here that the piston pin is offset to that side. so it's offset to the non-thrust side. This is really important, especially with the engine with a kind of a low stroke to rod length ratio like this. And what the offset does is it allows the piston to dwell at TDC a little bit longer, like a longer rod, and it kind of lays the piston more gently into the cylinder wall and not so much at a cocked angle. So it reduces both noise and wear and reduces friction. So we have a long rod for a stroker motor. We have our offset piston pin, and I'm hoping that that alleviates some of the negatives about having a stroker crank in this engine. Now, I think if you're a 4AG nerd, you call this a 5AG or something, but it's a stroke 4AG to me. I guess I'm not that kind of 4AG nerd. So our piston rings are a super low tension set. That's because it's a naturally aspirated engine. We're running kind of a high piston speed. So we're running a 0.8 millimeter number 1 compression ring. This is really thin, and a 1 millimeter number 2 ring. We can get away with this super low tension because of all the gas porting we're doing. The number 1 ring is steel, and it's nitrided for long life and good wear. Number 2 is iron with a Napier profile. Napier profile is like a hook on the face, and that allows the ring to break in and seat super quick. And the hook also scrapes oil off the cylinder face that maybe got by the oil rings. The oil rings are super low tension. They're like a 0.8 millimeter separator with 2 scrapers. So the ring package is a lot lower tension than we normally use. For our rings to have the longest life, we cryogenically treated them. CTP Cryogenics did it. Then we WPC treated them, so they'll have the lowest possible friction and the longest life. On the bottom end, we used to really struggle with the bottom end integrity on the 4AG, especially like when we were running them in GT3 and Formula Atlantic. We're revving, into the 9,500 RPM range. Now we would always have the main caps get all beat up, and the bearings get beat up, and we would have to service the engines at about a 3-hour of track time interval. After 3 hours, if you undid the main cap, the register would be all beat up, and the cap would just fall out of the engine, and the bearing would be all hammered, and the bearing would fall out, not even be retained by crush, and the bearing would look pretty worn out, like have signs of distress. 3 hours was about it. Like if you tried to stretch that, you'd be, pushing your luck about having a catastrophic failure. And TRD, we tried stuff to beef up the bottom end. Like we made a billet steel strap to go on top of the main cap. We tried ARP studs. All that helps some, but we would still, have problems with block integrity. Well, MRP solved that problem once and for all, because they've come up with this killer main cap girdle. Now what this does is it ties all the main caps together and ties the whole bottom end of the block together. So this bolts into the pan rail, and this bolts to the main caps, and it's like a solid billet steel. This prevents the main caps from moving at all, and also makes the block almost like closed in on the bottom. So it really helps the rigidity of the block and the bottom end. And I think if you're going to be revving past 9 with a 4AG and you wanted to live a long time, like if you're a street guy only doing it every once in a while, you probably don't need this. But if you do track days or if you drift, where you're on the throttle for long periods of time and you're revving really high for long periods of time, this piece of MRP is going to be a lifesaver, and I would say it's almost mandatory based on my experience with the integrity of stock blocks. It's a little bit hard to install. Like you replace your bolts with these ARP studs. Your machine shop has to have some skill, because what they have to do is shave your main caps so that all this thing lies flat, and it also lies flat on the oil pan rails. And then after you do all this shaving, you have to align bore the block, because this puts different stresses on it than just having regular caps, and you're going to maybe see some main board distortion. So your machine shop has to align bore. They also have to shave the caps to like fit it to your block, but it's well worth it if you're, you know, at high RPM for long periods of time. The part's not crazy expensive, but the installation, you have to have a skilled machine shop do it. Like your local auto parts store machine shop probably can't handle something like that, but just about any motorsport machine shop can do that no problem. The last thing on the bottom end is I got this Ross balancer. Now this balancer is made in Australia. It's an elastomer type balancer, but it's tuned for high RPM, not like the stock one. And it has like heavy duty elastomers that can be rebuilt. You know, like I always talk about how I want fluid dampers on everything. But fluid damper doesn't make a damper for the 4AG. But this Ross one is the motorsports grade damper for this motor. And it being a stroker motor, you know, it's going to have more vibration and whip than the short stroke motor. So I figured having the damper is going to be a good thing at high RPM. We're using ACL bearings. Now these are a good tri-metal bearing. Tri-metal means like you have your steel backing, then you have a layer of like hard alloyed lead. It's probably lead with tin, indium, and even copper as alloying agents to make the lead extra hard. And then it has a soft layer on top. So the hard layer gives the bearing more load bearing capacity than your typical bearing, and the soft layer on top gives you some embeddability like a stock bearing. I mean, it's not going to be as good for embeddability, but the load bearing capacity is going to be like twice as much. Embeddability means that if you have dirt or something in your oil, it'll embed in the bearing instead of grind into your crank. So, you know, if you have a lot of dirt in your oil, then having a high embeddability bearing is the thing. If you have a racing engine, having high load bearing capacity is more important. So these are bearings for a high load bearing capacity. For oil pump, we have a new Toyota pump that we took apart. Inside we're using Toyota billet gears. Now the stock gears, not sure what they're made out of, but they're known to break once you get into, you know, past 9,000 RPM, like 92, 93. They've been known to fail a lot. So we have the Toyota billet steel super strong gears that are, you know, good for at least 95. Some people say 10. I don't know about that, but I'm pretty confident it'll hold up and to not break at 9,500 RPM. We WPC treated the inside of the housing where the rotors ride in. We WPC and cryo treated the Toyota gears for slipperiness and more strength and durability. And we also WPC treated the pressure bypass spool valve. These things stick sometimes. You can lose oil pressure. So we wanted to make it as slick as possible with WPC so we don't have any risk of jamming, and if it's smooth, it can more accurately control your oil pressure. We also got a stiffer oil pressure bypass spring from SC Engineering. They're an Australian company. Now this is a smaller spring that goes inside your mainspring, and it keeps the pressure relief valve closed so you can have higher oil pressure. You know, you figure if you're revving that high, it's really nice to have a dry sump, but if you have oil pump gears that don't break and you have a stiffer spring for more pressure, that's going to help. We also radius the inlet and outlet passages in here to so there's less chance of forming cavitation in the pump. So we kind of went through the pump and made sure everything was cool and made sure that it was probably the best wet sump pump you can possibly do. So for our motor, our block required quite a bit more work than we normally do. We have our 20V 4AG block here. First thing we did is we took it to CTP Cryogenics to have it cryogenically treated. As I've said before, we've seen a tremendous increase in wear and strength and even friction reduction with cryogenic treating. Sometimes cryogenic treating can cause some slight shifts in dimensions, so we wanted to get it done before we did all of our machining. So after cryo treating, we bored our block to 82 millimeters. We used the torque plate and we used the same ARP studs to simulate bolting a head-on, so we distort the block in the same way that bolting the head-on would be. So that way, with the head on the block, we have nice round concentric bores for good ring seal. The 4AG is iron, but the studs are kind of short, and this block is kind of light and thin, so I really feel a torque plate does help on this. Like some beefy motors, it doesn't make that much difference. Like I think, B series BMWs don't distort that much, but other motors like small block Chevy or even this 4AG do. So we use the torque plate to bore it. Next, since we're fitting the bottom end girdle, we had to make sure that fit. So we fitted up the main caps, and our machine shop shaved the caps with the girdle to make sure the girdle would sit flush here and the caps would be all aligned, and the girdle would actually engage the caps. So that was a big operation. We used ARP studs on the bottom end, and with the additional torque and the distortion and shaving the caps and the redistribution of the load throughout the bottom of the block because of the girdle, that required a line boring. So the block was a line bored. After all that, we decked the block, and we did all of our honing. So we used a 480 hone, and then we did a plateau hone. 480 is a little on the coarse side, but we want the crosshatch to retain some oil. But the plateau hone takes all the peaks off of the honing pattern, so you still get a nice smoothness to it, and it's a pretty lustrous, smooth-looking bore, even though it's slightly on the coarse side. It doesn't look coarse. It looks really smooth. So after all the machining, we had the bores WPC treated. That really helps life and reduces friction. And the last step is we ultrasonically cleaned everything to get all the various media out of there. So quite a bit of work, but this block is going to be nice and strong and long wearing, and hopefully it'll help hopefully the block will be the cornerstone of us making pretty good 4AG power. So now let's talk about the head. This is a 4AG 20V head. It's a blacktop head. The blacktop heads have a little bit bigger ports, so supposedly they make a little bit more power. As you can see, there's 5 valves, 3 intake and 2 exhaust. So you have more total valve area. I kind of personally feel that the silver top 20Vs have a better combustion chamber because they have nice quench pads, and the blacktop has a more open chamber with very little quench. But the blacktop's known to make more power stock to stock, so I don't know. I had a blacktop, that's what I went with. I convinced Howard to come out of his head porting retirement and do me a favor and port my own personal head. Now, back in the TRD days, Howard's heads were the best at TRD, and his heads made the most power. And Howard's really good at porting, but he really hates doing it. So I feel kind of bad asking him, but Howard really likes the 4AG too, so he didn't mind doing this. So I always joke with him about this being his retirement head. But Howard did a really good job. If you know what a stock blacktop intake port looks like, he really narrowed up the dividers between the 3 valve ports. Now the outside port diameter is kind of kept small, so the velocity is high, but the dividers are narrowed down quite a bit, and the throat area past the dividers is opened up, and that's the biggest flow restriction area of this head. Also, he cleaned up the short side radius of all 3 inlet ports and kind of raised the roof in the area of the port dividers. So what he kind of did is strained out the port, kept the floor high, and kept the port entrance volume small. So he's creating a lot more flow, but keeping the velocity up, so we still make good torque and have a good power band. When you look, compared to a stock blacktop, you can see he's taken a lot of material out. And if you stick your finger into the 3 intake ports, like on the stock blacktop head, you can barely get your finger in there, but now it goes in there pretty easy. The short side radius is nice and smooth and enters the chamber nicely. So this is going to have a smooth, tumbling, uninterrupted flow coming in. On the exhaust port, it's the same thing. Howard opened up the exhaust port to the same size as the exhaust manifold gasket, and he really narrowed down the port splitter and really cleaned up the area on the radius into the combustion chamber and the entrance in there into the chamber. Now it's all smooth, there's no steps. It's actually opened up quite a bit, but the overall volume still stays relatively small, so we have good port velocity and good scavenging. So Howard doesn't just make it big. You know, there's a method to what he's doing. Howard also unshrouded the valves. Now we're running a millimeter bigger SuperTech valve, and you know that means the seating surface of the valve moves a 0.5 millimeter closer to the combustion chamber wall, and that can inhibit low lift flow out of the port. So what Howard did is he laid back the edges of the combustion chamber about 1 millimeter, so we have less shrouding from the combustion chamber wall than we did stock. He also took out that step between the valve seat and the combustion chamber, so the valve's not shooting out of like a crater, but it has a nice smooth transition into the cylinder. We also did a Newen valve job. Now the Newen is a CNC machine that cuts the valve seat. So the traditional, like a 3-angle valve job, is done by a 3-angle cutter. They'll have like maybe a 30-degree top cut, your 45 seat, and a 65 or 70-degree throat, and it just cuts those 3 angles. What a Newen does is it makes a continuous smooth radius from the chamber to the 45 seat, and from the 45 seat into the port. So this is the ultimate for flow, and it also can do some unshrouding depending on how it's programmed. It also can open up the seat. So in this case, it opens up the seat into the port, so we have a full unobstructed flow, which takes advantage of the big valves. Yeah, Howard did a bang-up job on this head, and you know, if you wanted to do it on yours and you're having us build an engine, MRP has a CNC ported version of this head that we can get for you, or we can also do a less intensive hand port job that will sub out, because I really don't want Howard to do this too much, because you know it's not good for his hands and all that. So we can duplicate it with a CNC head or a less extensively ported, hand ported head, but I'm getting the only Howard head. So you know, we surfaced this head and ultrasonically cleaned it after porting in the valve job. So I think this head will actually make quite a bit more power than stock. We're holding down the cylinder head with ARP studs. We're using ARP studs on both the main caps and the cylinder head. A lot of times you hear about me saying run stock torque to yield bolts on aluminum block engines. Well, the 4AG was done before they really had torque to yield bolts, and it's an iron block. So you can go ahead and use the studs. The stud will grow at the same rate with heat as the iron block, so you don't have to worry about additional distortion like you do with aluminum. I always talk about not running studs on aluminum engines unless you really have to, and that's because the stud grows at half the rate of the aluminum, and this causes the clamping force to really increase and could cause cylinder wall distortion, and puts a point load on the head gasket sometimes, which can cause less than optimal head sealing. That's why the factory uses torque to yield to make up for the expansion of the aluminum. But sometimes you just have to use studs with a lot of boost, and that's why machining with a torque plate is important in those cases. But 4AG iron block, use studs all day, and you can't go wrong. The other important thing besides the heads are the cams. So we're using Kelford 194C grind cams. Now this is their third from the biggest cam for this engine. It's big enough to where you're not supposed to use the variable cam timing control on the intake, but what we're going to do is we're going to limit the travel of the variable cam timing, and we're going to cut it down to 10 degrees of movement. And the guys at Kelford ran that on their computer, and they said it's okay, we'll still have the piston to valve clearance. But if you have a regular 20V, you can't go any bigger than their B cam. But the C cam is called their medium race cam. It's recommended that you have higher compression and a ported head to run it. So, you know, I think it'll be pretty good on this, especially with the bigger displacement. You know, we could probably actually go a little bit bigger and we'd be fine, but I want to make torque. So the 194C has 284 degrees of duration on the intake and 278 degrees of duration on the exhaust. The intake lift is 9.3 millimeters and the exhaust lift is 8.5. The stock lift is, I think, only 7.5 millimeters, and I think the stock duration is, don't quote me on this, but it's around 240 degrees, so it's quite a bit of a bump from stock. But the lift isn't as much as what you can get on the 16 valve. On the 16 valve, there's up to like 12 millimeters of lift on some cams, and that's all because the cam follower diameter. Like, you can't have too aggressive of a lobe, or else the lobe will go right off the edge of the cam follower, and it'll cock and get stuck, and it'll wear really quick. So that's one of the reasons why for peak power the 20 valve doesn't make as much as the 16. For the rest of the valve train, we're using SuperTech intake and exhaust valves. These are 1 millimeter bigger than stock. They're made out of nitrided 318 stainless. So when you look, the exhaust valve has a tulip contour, so it's kind of more like a cone. This helps the exhaust flow out of the head, and the intake kind of has a flatter nail profile on the valve. This helps the flow go into the cylinder better. Like, you look at the stock valves, they have the same contour in the intake and exhaust. It's kind of in between. The valves also have a turned down stem. The intake is turned down a lot more than the exhaust. The exhaust needs a bigger stem for heat dissipation, but the intake, it's all like really turned down quite a bit for more flow area into the head. Both valves are nitrided. Nitride is a surface treatment that makes a hard layer of iron nitride on the surface. It's kind of like hard chroming, but it's even harder. It's hard and slippery, so it won't stick, and it'll give really good life. We're running Kilford valve springs. You should always run the recommended spring from your cam manufacturer with the cam. That's because if you have a well-engineered cam like Kilford, the spring's harmonic characteristics matches the lift characteristics of the cam, so you can get more surge resistance with less spring tension. So, you know, never mix and match different aftermarket brands, at least in my opinion. The valve springs have been cryo-treated and WPC treated. This helps their fatigue life quite a bit. We're running SuperTech titanium retainers. These are a few grams lighter than stock. So I think our cylinder head's really good. I think it's going to help us with our goals of decent power and really good torque. The cam followers have been WPC treated to make them extra slippery, and the cams have been WPC treated, and the valves have been WPC treated. To seal the cylinder to the block, we're running a TRD metal head gasket. Back in the day, you had composite gaskets, and MLS gaskets were a rare thing, but this is probably one of the best performance gaskets for the 4AG. So in the past, one of the most vexing things about tuning 4AGs is the timing belt flaps around a lot, especially when you're running a cam with stiff springs. Now, back when I was at TRD, we just kind of lived with it and you know, changed the timing belt more. But today, with our engines pushing tighter and tighter limits, it's not acceptable to have the cam timing belt flop around, because it's making the cam movement irregular, and it's also throwing off the ignition timing. So as we're pushing engines harder and harder, we can't have fluctuating ignition timing and valve events. So MRP has come up with some stuff to eliminate that. First off is they have this mechanical tensioner. The original 4AG tensioner is like a wheel on the spring, and that allows a lot of flop. This is a solid mechanical tensioner, and it's not going to allow any flop at all. But you still have some harmonic whip of the belt. So MRP has come up with this roller that goes on the loose side of the belt that prevents it from flapping at all. This is a good part, but this is a CBY version of the same thing. And what I like about it is it uses a bigger roller with a OEM grade bearing. This is some kind of Toyota part. I'm not sure. We're only going to use the roller. So, you know, the big roller is easier on the belt, and the bigger bearing, OEM grade, will last longer. This is a good part, but you have to periodically inspect the bearing to make sure it's okay. And this will go for a really long time before you have to change the roller. And when you do have to change it, it's just a Toyota part that you can just buy. So, you know, that's how the cam flopping, the cam drive belt flopping around got cured. We're also running a Toyota heavy-duty timing belt. Like, this is Kevlar, and it doesn't stretch or mess around. So the belt itself doesn't stretch, and it's stronger. And between all of these, I think we cured the 4AG belt flap issue. So when we're building an engine that can rev to 9,500 RPM, oiling is really critical. Like, when you reach like 9,500 RPM, that's about when you start to need a dry sump, but I don't want to buy one for my car. They're expensive. So I'm taking a lot of time to do the wet sump system with a lot of detail. The first thing is a Moroso oil pan. This has wings. It has like about a quart and a half extra capacity. And it has a vertical and horizontal baffles. The vertical baffles have these trap doors, so oil can flow toward the pickup, but not away from it. So this helps maintain oil pressure under heavy quartering load. So this pan helps oiling quite a bit over stock. To help out the oiling even more, I'm running a crankscraper.com crank scraper. Now this scrapes the windage cloud off of the crank and returns the oil to the pan quicker. And also reduces the total amount of windage. So this is cut to just barely clear the crankshaft and to skim the oil off of it. And I also have this little Teflon part here. This we can like hand cut to get it really close to the crank and really reduce that windage cloud. Sort of like some of the stuff a dry sump has, but this is for the wet sump. This will get all the oil back to the pan quickly. We also have this bigger volume pickup that's longer for the Moroso pan, and it has a sturdy welded in strainer, not the weak screen that sometimes gets sucked in like the stock one. It's also quite strong, so it won't break like a lot of stock pressed together and brazed pickups. So we should have pretty adequate oiling even though we're revving really high. For induction, we're using the factory ITBs. Now the factory ITBs are kind of big. They're 45 millimeter on a black top, so it's a couple millimeters bigger than a silver top ITB. We had Cusha House restore these. They took it apart, cleaned them, rebuilt them, resynchronized them. The results are really amazing. I mean, these things are all corroded and gross, but when you look at them, they look almost better than new. Like all the steel parts have been re-zinced, I think. I mean, with a real hard, shiny zinc plating. I mean, it looks real brand new. I think the all the aluminum parts have been vapor honed, and they come pre-set up and ready to go. Now, everyone I know that has used Kyushu House has nothing but raves about them. Like, their primary thing is restoring side drafts or vintage cars. And I've seen some of his Mikuni restorations, and they look really awesome. I mean, this looks really awesome. And everyone I know has raved about how well his remanufactured carbs work. I mean, this is like great. It's like better than new. What can I say? So for our ITBs, we got velocity stacks from T3. T3 makes velocity stacks for the silver top and the black top. The difference is the ones for the black top have a bigger ID. So they're not as long as what could be optimal for the best performance, but we do have clearance issues with our stock clutch master cylinder, and we wanted to run a big enough filter, so this length will allow us to run a ITG foam filter. Now, you always want to have about 4 inches of clearance between the end of your stacks and whatever parallel wall, and these filters give you that clearance, and it just will barely fit into the engine compartment of our A86. So we can have stacks, ITBs, and a decent filter. To adapt the 20V into the 4AG, we got some parts from Flows. Flows is a company that specializes in 4AG parts and A86 parts. So they make these water system parts to help adapt the 20V into the A86. Now, the 20V is originally an engine for a front-wheel drive car, so the water outlets and thermostat housing all are in the wrong place. A lot of people make the mistake of just putting a block-off plate in the rear, but you actually have to have water going between the head and the block in that area. So, you know, otherwise your number 4 cylinder runs hot, so it's not really the best to just put a plate. So the Flows kit takes care of that. Also, Flows makes a kit to block off the EGR passage on the stock ITBs, and they make a crank angle sensor kit that gets rid of the distributor. Otherwise, you have to cut the firewall and make a box for the OEM distributor. And we're going to go distributorless with direct fire ignition, so we're not even going to need a distributor anymore. I got this slick looking valve cover from CNC Innovations. It's machined out of billet. It's kind of heavy, but I almost don't care because it looks cool. It has all the baffling to prevent you from blowing your oil out of your vents, and it has built-in brackets for direct coil on plug ignition. So for our coils, we're using Ignition project coils. Now we've used this on just about all of our serious project cars. These things have about twice the spark energy of your typical stock coils, and at low RPM they have multi-spark capability, kind of like an MSD ignition. They fired the spark plug multiple times on each power stroke, and this helps you ignite the mixture, and it's pretty handy if you have a big cam with an unstable idle and all that. These things make a big difference, and they're a really easy way to bump up your ignition power. It's like getting an MSD and a hot coil all at once. We've run this on many of our project cars, and they do a lot to clean up misfires, and cars idle better and have better bottom end response and stuff with these. You can also run more boosts without misfire, but that's kind of not a thing with this motor. But our valve cover will let us go directly in there. They even have notches so we can tuck all the wiring inside under this cover. It's going to look really clean. For a header, we're going to run the Martellus XL header. Now this header is one of several that they make for the A86, and it's the one that's designed for built engines, bigger displacement engines with more power. They have other ones with smaller primaries for like more stock engines, but the main difference is that this has larger primaries. The tune length is a little different. I think the first merge is a little shorter to run with the engine with a bigger camshaft. The construction of this header is pretty good. It's CNC flanges. It's all TIG welded. It's made out of a high quality stainless. All the welds and everything are hand finished on the inside for less turbulence. All the joints are merged, and it's a nice, knife edge true merge. It's a really good header, and it goes right in. One of the reasons we got it is the header's designed to work on both the 16 valve and the 20 valve. The 20 valve, the rear cylinder number 4, the exhaust stud is in a slightly different spot. So this header has 2 holes to accommodate the 20V, and that's kind of like the main reason why we got this header. For our flywheel, we're running the Toda steel flywheel. Now, this is a really light flywheel machine from a forged billet. It has holes around the periphery to reduce rotating weight, reduces the inertia. It's light, high quality. We had it balanced, and we cryo-treated it with CTP cryogenics to give it some more abrasion resistance and longer life. We're holding it to the crank with ARP studs. When I was at TRD, we did have a little bit of a problem with shearing the flywheel bolts off on some of the GT and Formula Atlantic cars. It wasn't a huge problem, but it probably happened 5 or 6 times. So at the time, we commissioned ARP to make flywheel bolts for us, and I believe these are the original TRD spec flywheel bolts. Here they are many years later, still being made. So these are stronger bolts with a non-threaded shoulder that fits into the flywheel real good, that should stop any flywheel bolt shearing issues. So that about wraps up our 4AG, 5AG, 20V engine build. Now, this is a really extensive build. I'm really excited. You might sound a little bit disappointed, but I'm predicting this will probably make 175 wheel horsepower, which is actually quite a bit for a 4AG that's streetable. That's probably more than 200 crank horsepower. And I mean, even the Formula Atlantic motors back in the days, they made about 230 with a real narrow, unstreetable power band. So this is going to be 200 plus horsepower with a nice, wide, friendly power band. And it's going in the car that's probably going to weigh about 2,200 pounds. So, you know, it's not the end of the world. So if you like this content, please subscribe to our channel, give us a like. If you want to support us, you can become a member. Now, we don't get paid by anyone to do these videos, even though people think we do. And YouTube really doesn't pay very much, considering how small we are. So if you want to support us, help us keep on coming out with this great content, you can become a member. There's a link that you can click on, and you have certain perks. So support us, become a member. You don't have to, but we really appreciate it. So until next time, I'll be talking to you later.